A students.
B's name.
All right. Chains and sprockets is the next topic of conversation. V-belts and flat belts have some distinct disadvantages. They have some advantages. They're relatively inexpensive. The disadvantages are that when the belt stretches, they tend to slip. Or if you're in a watery environment, they tend to slip. Or if you're in an oily environment, they tend to slip. A more positive transfer of power comes about when using sprockets and chains. So I've got a little bit of stuff on sprockets on my mechanisms DVD that I have. They use a fair amount of examples of motorcycles and bicycles for sprockets and chains. That's not necessarily the only application that you will find. Used when no slip, such as direct positive drive is essential, such as on a bicycle or a motorbike or any other kind of a drive that you really need to have positive transfer of power. Sprockets. Sprockets are TuTh wheels attached to the driver and driven shafts. Again, they're using a bicycle with the multi-gear ratio changing, quick speed changing apparatus on that. In industry, it's not, I mean, there are certain examples of that, but a lot of times it's sort of a one-to-one driver and driven. So you will find the same sort of aspect to that as we did with V-belts. You have a driver, you have a driven. Generally speaking, the driver is the motor, and it's spinning at a higher RPM than the driven, which is some piece of equipment that has a larger sprocket to it and reduces the speed down. And again, based on the sizes, you will see that there is a ratio between the diameters. The smaller diameter spins at a faster speed and slows down the larger drive and has a more positive application there. All right, chains. There are lots of different types of chains that exist in the world and in industry. You can read in the textbook, you should read in the textbook about the different types and styles of chains. So I won't bore you with all of that, and I will sort of expect you to look at that. This is a roller chain, which is highly prevalent in industry for the chain drives that exist out there. It's important that the chain is tensioned correctly to prevent it becoming disengaged from the sprockets. This can be done on a bicycle by moving the position of the back wheel. Obviously, if I have a really slack chain, with a lot of slack in it, I run the potential of it becoming disengaged and I'm losing my power transfer ability. Velocity ratio of the sprocket in the chain system, determined by comparing the number of teeth. Let's close that guy. All right, remember this from V-belts. We took the diameter of the driven pulley and divided it by the diameter of the driver pulley because, generally speaking, we divide the larger number by the smaller number and get a positive number at the end, which is the speed ratio. So if I need a speed ratio of 1 to 2, the diameter on the driver is going to be 1, the diameter on the driven is going to be 2. Or if I have 10 teeth, I want 20 teeth, something like that. So the speed ratio. So here we're doing number of teeth on the driven divided by the number of teeth on the driver sprocket. Very similar to what we did. There's also the fact that these chains, they do loosen up over time. The sprockets themselves will start to wear, and the chain itself will start to lengthen just a little bit, not quite as much as a V-belt, but they do become slack. And if that's the case, then I might want to put a little idler mechanism in there. We're going back to our derailleur. and we're seeing that there's some ratios in here, 14, 16, and 18. And if I put that in motion, this is generally on, it can be adjustable. Sometimes it's on a little spring mechanism, sometimes it's an actual mechanical connection that's gonna make that, put a little more tension on there, which keeps tension on where I'm driving this from. And similar to the V-valve, where we had a tensioner in here, they're calling it a jockey wheel. Lots of times it's called an idler wheel. So here's another one of those nice pieces of farm equipment. This looks more like a flat belt, but it might be a roller chain. And here there's a mechanical mechanism, there's a bar, and then there's another bar that can be loosened and tightened, and that can be adjusted to put tension on that. It looks pretty floppy even as it is to me.
Really
But
sketchy.
you know, that old farm equipment kind of works forever, it seems like. Alright, and that's just about it for what I have for sprockets in this particular case. Alright, now, the part that comes next is what you're going to have to keep your head on straight over. Let me blank this. There's, of course, calculations that get to be made. You were sort of expecting that, I think. So we determined with V-belts the diameter based on the horsepower and the revolutions per minute. We had charts and tables to look at. We have more charts and tables to work out when we figure out what chain drives are supposed to be. And I need to go through the example problem and then talk about the actual project itself. Beginning on page 14 in the textbook, which looks like this. Come in a little bit. We don't really need to look at the lamps. We need to look at the chart. The first chart that you're going to encounter on page 14, ultimately we're going to be using this formula in here to figure out what the length of the chain is going to be. It comes out to be 2c plus m over 2 plus s over c. C is the center-to-center distance between the motor and the piece of equipment that's being driven. M is the number of teeth in the driver and the driven sprocket that is added together, divided by 2. S comes from finding out what F is. You find out what F is in the formula by subtracting the number of teeth. Larger number of teeth, subtract the smaller number of teeth, and you get a number. Let's say it comes out to be 10 for F. F's not in this formula. F is something that we find by calculation. The number 10 then gives us, so I have a column for numbers that would fall in that calculation, which equates to a number that comes in the next column over. So 10 would give me an S number of 2.53. That's how S is determined to put back into the formula to figure out what the length of the chain is. Confusing? A little bit. But you know what? That's how chains are calculated. I could go to a chain catalog or to a website and I could pull it up and ask for how do I figure out what the length of a roller chain is. I'll get some, maybe the letters aren't quite the same, but it'll be that variation of formula in there. And that's just, and then there'll be a chart that has an F value and an S value, and the rest of them are calculations. Okay, don't keep your questions for now. It will become clear as mud when we get further in. Okay, honest. It'll, well, maybe a little clearer than that. Down at the below that is another chart that, again, with V-belts, there was a chart that talked about service factors. What kind of service factor was involved with what kind of equipment was it? here we have the type of driven load. Now with chain drives I can have a smooth drive situation. I can have one that has a moderate shock. It turns on, it turns off. I could have a heavy shock. There might be a lot of turning on and turning off. There might be vibration involved with it. So there's a certain type of load that's determined. The type of input power, internal combustion engine with hydraulic drive, electric motor or turbine, internal combustion engine with mechanical drive. I might have multiple strands. I might have a single strand. If I have more than one strand, chains that are stacked up, then I have a multiple strand factor that goes into figuring out what the actual design horsepower is going to be based on the original horsepower and any kind of service factor that I have to apply to that formula. So we'll go back and we'll take a look at that. Next page in, page 15, is a chart that you don't have to worry about because it's for kilowatt, which is metric system. So kind of put that off to the side. Page 16 is another kilowatt rating chart. We don't really have to pay much attention to that. When we get to page 17, then we're going to pay more attention. I have 3 different charts on this page. And on the charts, I have at the top, let me get a little closer here. I have something that's called a number 35 ASA standard roller chain. And a number 35 is assigned a pitch of 0.38. Pitch is the distance between the center to center of the rollers. And that's what generates the spacing. If I have a number 35 chain, I'm going to need number 35 sprockets so that they match up. So the chain actually fits inside the sprockets and everything rotates like it's supposed to. If I have a number 40 chain, it's going to be a 0.5 pitch. Just like a type A V-belt has a certain width and a certain depth to it, and a type B and a type 4L and all those different kinds of designations for the V-belt, it's the same kind of situation when I have a roller chain. So I've got a couple of different charts that talk about horsepower. Page 18 is just another one that has additional chains, 50, 60, and 80, and they go up from there. Then on page 19 I have another scary looking chart here that is actually going to be used to start the calculations. I have up here I have number of strands, chain strands, 1, 2, 3, and 4, and these are horsepower ratings along the left hand side. Design horsepower over here, which takes into account any kind of service factor I might have, and then down across the bottom is the RPM of the small sprocket. Every once in a while the small sprocket is going to be on the driven or the piece of equipment because they need to speed it up versus the RPMs on the motor. That doesn't happen very often. So I'm going to make a comparison in here. When I have horsepower and RPMs that intersect, it's going to fall into one of these bands. 30, 25, 35, 40, 50, 60, 80, 100, 120, 140. That tells me what type of chain I have. So if I get an intersection in this band in here, that would be for a number 60 chain. It should have a certain pitch to it. And then I go from there and figure out the size of the sprocket. Page 20 is the kilowatt equivalent of this chart here. So I don't have to worry about that. The next chart on page 21. U.S. Custom inches and millimeters. So here, once I find out what type of chain I need number-wise and what type of pitch it has, and then when I start determining what the number of teeth are in the driver or the driven sprocket, I come over to this chart to look at the number of teeth. Let's say I had 15 teeth on one of my sprockets and a 3/8 pitch chain. That means that there's a maximum bore size that exists in here of just over 7/8 of an inch, which means that if I have a shaft that's larger than that, I'm going to have to go to a different size chain, or maybe custom make a sprocket that has the ability to take that kind of bore. Or get a motor that's got a smaller shaft to it. Any number of things could happen. So, question?
Or mill the shaft.
Well, yeah, I mean, there's things that can be done, but basically if I can stay within this maximum bore in finding a supplier that has a sprocket, I'm much better off. And so that's a metric down below that. And then on the last chart that we would be using on page 22, number of teeth on the sprocket. So it lists a 25, 35, 40, 50, 60, and 80 chain. It's to my advantage in a design situation that if I can go to a supplier that has these number of teeth already made, it's sitting on the shelf, I get a catalog number, I order it, and I can put it into my design. So sometimes I run a design calculation that comes up with a certain combination of teeth, 20 and 30, let's say. So I go in and I look on my particular chain, like at number 50, okay, there's a 20 that's available, and there's a 30 that's available, so I can use that in my design. So let's say my calculations come up with a 24 and a 83. So maybe I've got a 24, but in that chain I don't have an 83 number of teeth. Maybe 84 will work. Maybe 80 would work. Or I'm really sensitive about my design and I want to have an 83 tooth sprocket made. Companies will be happy to take your money and make you a custom made sprocket. But if I can go and buy one off the shelf, again, I'm much better off. I'm further ahead in what I'm trying to do design-wise. Okay, so it's kind of like this level right here. I have no idea what you're talking about, and now we need to go through an example problem. The example problem starts in the textbook underneath this little kilowatt or this little horsepower rating chart. Example number 1. This is information that you might get in a design situation. So select an electric motor-driven roller chain drive to transmit 5 horsepower from a countershaft to the main shaft of a wire drawing machine. Countershaft is 1.5 inches in diameter and operates at 1200 RPM. The main shaft is also 1.5 inches and must operate between 375 and 385 RPM. Shaft centers, once established, are fixed and by initial calculations must be approximately 22.5 inches. The load on the main shaft is uneven, presents peaks that place it in the heavy shock load category. So that might be a design situation that you would run up against. Does that sound familiar to our V-belt?
Yeah.
This would be the appropriate response, yes. Because we're looking at horsepower. We make an adjustment in the horsepower to get the design horsepower. We look at the RPM of the motor and the RPM of the piece of equipment.
It's like a safety rating.
Calculate diameters. Now, to prove to you that this is a pretty common situation that exists in the real world, so let's do this one. I'm searching for that. This is it's almost more like, it's kind of a roller chain because it's got a flexibility to it. This is a multi-strand chain that might exist. There's more surface area to it. There's more sprockets that would generate a bigger, more positive power transmission. Those do exist. This is a roller chain. And it's got bearings and it's got bushings and it's got side links to it. And there's one link in here somewhere that can be taken apart so that I could take this off if I needed to get it onto the sprockets, or if I needed to replace it. Ah, there it is right there. There's a little flat cotter pin kind of thing right here that can be taken off, and then that little connecting link can be separated. They come in pairs. And when we get into calculating the length of a chain, we try to come up with even numbers. And so you'll see that in the calculations. They're pretty precisely made. There's probably a YouTube video. I don't think I pulled it up when I was doing drafting fundamentals at all. But it's kind of interesting to watch how roller chains are made. You might want to go back and look at that. And then this would be a sprocket. This sprocket has a hub, an outer diameter here, and then it has a bore size in here. Now, this has got enough material on it that if this bore was too small for the motor, I could machine it out, I could drill it out, ream it out, and use that. There's no keyway, there's no hole drilled in here to put a big old long set screw. There's no mechanical way of connecting this to a shaft. It would just literally spin, which is, it's just sort of a blank. This has a certain chain number to it. I don't have a roller chain that actually matches up with it. I thought I did, but I have lost track of it somewhere. And I've got another chain that I'll just show you. I won't pass it around because it's really kind of oily and greasy to keep it from corroding. And it's a length of chain. So you can buy chains that already have a specified length to it. And this one, basically, I can just pull this out and make it to the length that I need it to be, and then put a connecting link in it to make it to the length size that I want. This one happens to be, looks like a 35. It's 10 feet of chain. So there's that variation as well. And I don't really want to pass that around. It doesn't fit with anything, and it's kind of ordered.
What do they call that? Like the master link, right?
Master link, yes. There's probably other terms for it as well. And then there's also two little tools and things that that you can work with. All right, so let me go back before we actually get to the sample problem. And I've got some pages out of old catalogs. That talk about functions of roller chains, transmits positive power, 98% efficiency, high versatility, shock absorbing ability, lightweight and compact. Some characteristics that V-belts and flat belts don't have. Two important factors would be considered when determining the quality of any roller chain: resistance to wear and resistance to fatigue. So the wear is going to come with the rollers as they react with the sprockets themselves. That's where the wear is going to come in. Or the side links can fatigue and fracture, failing through fatigue. There are calculations that can be done, which we're not going to worry about. A roller chain is basically a series of journal bearings connected by link pins. Chain flexure is a term applied to the flexing movement of the journal bearings as the chain engages and disengages the sprocket. So there's some formulas that you can calculate, because there's a certain rotation to this and there's certain tension and non-tension aspects to this chain. This is kind of the slack down here. And we can calculate, because you don't want this to disengage in this area in here and reduce the efficiency of the design. This is an example of some types of connections for the master link. A solid, long solid cotter, a riveted pin, double cotters, a long cotter pin. There's also a little, going to have a connecting link, which is what's on the chain that's kind of going around, and cotters on a connecting link. So there's different ways of doing that. There is the ability, using an offset link, to, if you had an odd number of pins in the roller, that you can make a connection with just a single versus a 2-pin. But it's not as common. You know, the millwright or the mechanic may not have all those as handy in his little toolbox to fix the chain. A little more specialty type situation on that. And this is a Morse catalog that I've had for years and years. Roller chain horsepower rating. So you can see that they have their service factors in here. Smooth, moderate shock, heavy shock. internal combustion engine, hydraulic drive, electric motor, turbine, internal combustion, mechanical drive. Very similar to what's in the textbook, a little more, maybe a little more simply stated. But if it's smooth, there's no service factor involved. Moderate is 1.3, heavy is 1.5. That's a multiplier that you multiply the original horsepower by. And then it shows different classifications of pieces of equipment that you might encounter. Bakery machinery might be classified as a moderate shock. Brick and clay machines, heavy shock. Conveyors, apron, bucket, elevator, heavy shock. So I can go in and I can take a look at their engineering information. If it doesn't show up anywhere, I get on the phone, I call a salesperson. I say, here's my situation. What would that be determined? Smooth, moderate, heavy? What's the designation? And then we'll get to this in the sample problem, but horsepower ratings, standard single strand roller chain, number 25, which has a quarter pitch. We're taking our revolutions per minute, we're coming down and trying to find where our design horsepower exists in that column of RPM, and this comes over and tells us what the number of teeth are going to be when I start my design process. And of course there's many different pages out of that catalog that I have factors that I can look at. And I think that's about it until we get back into, oh, this is one other one. This is another type of service factoring that is available. Let's see, is there anything? Well, dough mixers was kind of like that bakery equipment. So AC motors, normal torque, normal service, dough mixers, they're going to use a 1.2 service factor on that. So the information is out there, I just have to find it. If that's what I'm being asked to do, is to calculate in sizes of chains, sprockets and things, which you might end up getting to do, having fun doing that. All right, back to our sample problem. So to start this, we look at the service factor. The corresponding service factor from figure 20-2-9 for heavy shock, load, and electric motor is 1.2, and I've covered all that up, of course, with all my messing around here. So let's get out of there, come back to these pages. All right, so that came out of this chart down here. So they said it was going to be intermittent load and it was going to be a heavy shock. And it's electric motor and it's going to be the 1.5 service factor. Everybody seeing that okay? All right, so we're going to take our design horsepower and multiply that by 1.2. If I can find the page that that's on. So let's switch over to here. Alright, so the next page over just talks about design horsepower. You take your 5 horsepower, the original horsepower, multiplying by 1.5 to get the 7.5 horsepower. Now you start looking at your chain selection, which is going to ultimately lead you to finding out what the number of teeth are. On the horsepower rating chart, the suggested selection using a design of 7.5 horsepower and 1200 RPM sprocket is a number 40 chain or a 1/2 inch pitch chain. Now, how do you get there? You go back to the chart that has horsepower, which is going to be this chart right here. And I gotta come out just a little bit. That's on page 19. So on the left-hand side, I'm gonna come down until I find there's 7 and there's 8 on the chart, so that's 7.5 right here. I'm gonna go horizontally across from that, which is 7.5. I get a horizontal line. And then I look along the bottom until I find my 1200 RPM, or whatever the motor rating is, and I do a vertical line up from 1200. And where the 7.5 and the 1200 intersect, it falls in this band right here, which makes it a number 40 chain. Easy enough so far? Okay. So then we continue on from there. All right. We don't have to worry about multiple strand factors on that. So then we go over here to the next part, step 4, final selection of chain and small sprocket. On the horsepower rating table for a number 40 chain at 1200 RPM, the computed design of 7.5 horsepower is realized with a 20-tooth sprocket. We go down the column headed by revolutions of the small sprocket, 1200, and find the nearest value to the design horsepower. Follow the line horizontally to the left to find the number of teeth for the small sprocket. So I have to go back and find my number 40 chart, which is back on page 17. All right. So I got the 40 from that horsepower chart, fell in that band. So I go back to the number 40. Then I look for the RPM of the small sprocket, which happens to be on the motor, and I come down here until I find the closest number to 7.5, which is my revised horsepower due to the service factor. 7.69, I come across here and I see that there is 20 teeth on the small sprocket. Sorry that this thing goes in and out wise, but I have no control over it.
2006.
All right, everybody okay with that so far?
I missed that.
Okay, the number 40 I got from the first chart, where 7.5 and 1200 intersected in that band of 40. That means that I need to use a 40 chain. So I go to this chart, which is a number 40, which is a 1/2-inch pitch chain. I go to the 1200 RPM, I come down until I find the number that's closest to the horsepower. I design horsepower, I come across here and I find the number of teeth. If I were doing a V-belt, I'd be RPM of my motor, and I'd come down, find the design horsepower, and I'd find out what diameter the small sprocket was supposed to be. Pierce.
So for that first one, which was the service factor, the difference between like, the different service factors, so that's kind of accounting for like a higher horsepower?
It's not accounting for a higher horsepower, it's accounting for the type of loading that's going on.
Right.
Is it
okay.
smooth, there's no interruption in it,
Okay.
there's not a jerky start and stop, or there's not a lot of vibration or anything like that. It's more that factor.
Okay.
What kind of equipment? More like, is it a furnace, is it a drill press, is it a power machinery, you know,
Right.
metal cutting equipment, that, like the V-belt was. Okay, so that's, and then I have to adjust it according to that, which in a sense does bump that horsepower up.
Yeah, because yeah, just like how it's 7.5 and stuff.
Meaning the 5 horsepower, because of the heavy loading, might wear out faster.
Right. Okay. Yeah.
And I have to then design according to that.
Gotcha.
Okay? All right, I have the number of teeth. I now have to determine what is the speed ratio, so that I can determine how many teeth I need on the larger sprocket. the driver is operating at 1200 RPM, the driven at a minimum of 378 RPM. The speed ratio becomes 1200 divided by 378, or 3.17 to 1, minimum. So I'm always kind of designing to the minimum values. Therefore, the large sprocket should have 20 teeth, which is the number of teeth on the small sprocket, multiplied by the speed ratio of 3.17, gives me 63.4 teeth. Well, I'm probably not going to get 63.4 teeth. Since the standard sprocket sizes near this number of teeth are either 60 or 70, which takes me to one other chart. Alright, so I've got 20 and 63.4 for a number 40 chain, which is in this column right here. Now, what turned up yesterday in the class was people thought that maybe there was a correlation between the numbers in this column and the numbers in this column. And I needed, if I had a 20, then I should try to find a 51 or 50 or 52. There is no correlation. This is just numbers. Down to 38, they ran out of room. They didn't want to make the column twice as long, and they just started another set of numbers over here. There's no, if it's here, it needs to be over here. It's just, these are the number of teeth that are commercially available. I could go find these at McMaster-Carr, or Bearings Inc., or Power Transmission, or something like that. We have 20, and we have 60, and we have 70. You know, it's not going to work very well. I could go have a sprocket made that had 63 teeth on it, but if I can get one that's commercially produced, I'm better off. I back up one step. I go back to my 40 chain, half-inch pitch, 1200 RPM. I come down here and I go, okay, what other number is a little closer to my 7.5? Well, there's 8.11 and there's 7.27. 7.27 is a little closer than the 8.11 would be. So I'm going to go and take that and come across. Now I have 19 teeth as my initial selection. And I run my speed ratio on 19 teeth. In rechecking the smaller sprocket, 19 tooth sprocket would also be acceptable. This would require a large sprocket of 19 times 3.17, my speed ratio, or 60.2 teeth. Bingo, I got it. I can go 19 and I can go 60. And I can get really, really close to my speed ratio, which was what I'm after. They're commercially available. There's a 19 that's available. There's a 60. If you went back and looked at the charts, the maximum bore diameter would fit inside of those, and it would be fine. So it's more economical to use those combinations. All right? Everybody set on that? Okay. Now we go to the formula. 19 and 62 sprockets are placed on 22.5-inch centers. Calculations are as follows. Chain length in pitches is what we're coming up with. 2C plus M over 2 plus S divided by C. C is the center to center distance. So I've got 22.5 what is that, plus the pitch?
I think it's divided by 0.5.
Center fit distance divided by the pitch. Okay, I'm sorry. C is the center distance divided by the pitch. That's going to give you the C. So 22.5 divided by 0.5 is equal to 45. That goes up in here. M is the total number of teeth on both sprockets. 19 plus 60 equals 79. That's M. The S value is obtained by finding F first. 60 minus 19 is 41. I go back to the first chart. I find 41. Yeah, I'm in my F columns, down to 31. I come over here, I find 41. I look over here, my S value for that is 42.58. That's how I determine what the S value is. 42.58. I substitute the values. So once I get C, I go 2 times 45 plus 79 divided by 2 plus 42.58 divided by 45, which is C. I end up with 130.44 pitches as my chain length. I am looking for an even number of pitches. So I'm going to take 130. I might get 131 something. So then I'm going to decide, okay, can I go with 130 or could I go with 132? How much leeway do I have in separating the two center distances? Well, that may be determined by the actual length of the chain. And then I can make that adjustment and then fix the center to center distance based on the determination and calculation of the chain length. So it's approximately, I have some leeway in there. Once I have the number of pitches, coupled to an even number of pitches, we're going to use 130. And we have some leeway on the center to center distance. The final step is to take the chain length in pitches, the number of pitches times the pitch of the chain. Number 40 has a ½ inch pitch. 130 times 0.5 is 65 inches. I go out and I look for a roller chain, a number 40 roller chain that's 65 inches in length. And I'm done. As easy as that, he says, confidently. Haha.
Fingers coffee.
It works, okay? Don't scoff yet.
Like I said, clear as coffee.
All right, and back in D2L
Like that's his butt.
on the assignments is chain drive calculations. It's not going to give me the right thing because I'm not logged in as a student, but you go to that link, you download the document, and you do the calculation for that. Save it as a Word document, upload it back into D2L, and we're on our way. All right, questions concerning that?
Yeah. What does F look like? Like I did.
F is simply
How do I
the
recognize
number of teeth subtracted from each other.
How do I recognize that in a paragraph or in like a? I don't know.
Well, first of all, you have to determine how many teeth both sprockets are going to have. And then you just subtract the number of teeth. So it might be better if I work with you more individually on the next, when you're working on that actual design calculation, and then I can help you with that. That's what F is, and you need to get F to determine what S is from a chart. Okay, I'm going to take just a very short break in the videoing because it worked better yesterday if I broke it up into two. This is for assignment number 3, the calculations for assignment number 3 in the assignment folder, and then I want to start talking about assignment 4 to work on, so let me